This screencast is on molecular shapes. The arrangement of pairs of electrons around the central atom determine the electron arrangement and the resulting molecular shape. If you have two pairs of electrons, the electron arrangement is referred to as linear. If you have three pairs of electrons in the central atom, the electron arrangement is referred to as trigonal planar, and then tetrahedral represents four pairs of electrons around the central atom. And it's a little harder to visualize, but if you look at this spinning molecule, you can easily visualize that there are indeed four pairs of electrons. And according to the VSEPR theory, or valence shell electron pair repulsion, all of these electrons repulse each other equally, and you get these well-balanced geometric shapes. And here we have carbon dioxide, here we have boron tetrachloride, and then last we have carbon tetrachloride. Let's look at the shapes of the molecules themselves. The first shape, if we have an electron arrangement that's linear, which means it has two pairs of electrons around the central atom, the resulting molecular shape is always linear. First, you need to look at the Lewis dot diagram. Once you can see the diagram, you can visualize what the molecule looks like. So we have carbon dioxide here, we have nitrogen dioxide ion. We just have to add an electron to this Lewis dot diagram to get it to balance. Then we have the very interesting beryllium hydride molecule, which is used in rocket fuel. And this is interesting because if you look at your periodic table of elements, which you should have here handy, you'll see that hydrogen is bonding with a metal versus a non-metal. And covalent bonds are normally two nonmetals, and this just happens to be an exception. And these atoms actually bond around beryllium in different manners as well. Let's talk about the trigonal planar geometric shapes, which are determined by the electron arrangement next. When you have three pairs of electrons, they balance themselves uniformly around the central atom. And if you have an atom associated with each of the pair of electrons, you get a trigonal planar molecular shape. If you have an atom that's missing, you'll get a bent shape, which we'll talk about in a moment. So first, we draw the Lewis dot diagrams, which are represented here in the magenta colors. And we have boron hydride, the carbonate ion, and then the common formaldehyde molecule. When we get into electronegativity and the polarity of molecules, you'll see that this molecule is nonpolar and this molecule is polar. And it's based on the atoms around the central atom. And there's a screencast on that specifically. And you'll see that the molecular shapes are independent of whether there's one or two pairs of electrons associated with this atom on the outside here. So we could have either one or two pairs, so we could have a single bond, a double bond, or we might even have triple bonds. The only thing that matters is that it has three pairs of electrons around the central atom. That always determines a trigonal planar shape, and if the atoms are also associated with each pair, that results in a trigonal planar shape. Let's look at the next example of a trigonal planar electron arrangement, which is the bent molecular shape. And it just has the same number of electrons, as you can see from the Lewis dot diagrams. It's just missing an atom in one leg of the trigonal planar geometry. So it results in a bent molecular shape. This bent shape has three pairs of electrons around the central atom. And we have the nitrate ion, the chlorine dioxide cation, and we have ozone. Both ozone and the nitrate ion are resonance structures, meaning this dot diagram can be drawn two different ways. The first way is like this. The first result is like this. And if we do a mirror image of this, we get a resonance structure. And the same can be said of the ozone dot diagram. And then the chlorine dioxide cation just means that we have to take one electron away from this Lewis dot diagram to make all the atoms balance with the 8 electrons in the valence shell, which is typical. Next, let's look at the tetrahedral electron arrangement. And we have methane, carbon tetrachloride, and the ammonium ion. All of these have 4 pairs of electrons around the central atom, and each of the electrons also have an atom associated with them. So we have well-balanced, nice geometrically shaped molecules here. This ammonium ion happens to have a positive charge because we've taken 1 electron away. If we take 1 leg of the tetrahedral away, the resulting shape will be the next molecular shape. That would be a trigonal pyramidal shape. It looks like a pyramid versus trigonal planar. And it still has the 4 electrons or 4 pairs of electrons around the central atom. And we have ammonia, phosphine, and the hydronium ion. And here's the associated Lewis dot diagrams. The last electron arrangement that is tetrahedral is the bent molecular shape. In contrast to the trigonal planar bent molecular shape, these atoms have 4 pairs of electrons around the central atom. And most important, we have the water molecule, which is a polar bent shape, and it behaves how it does because of its polarity and its shape. We also have hydrogen sulfide and oxygen difluoride, and we have all the associated Lewis dot diagrams. In addition to the molecular shapes we've covered, there are other shapes which for this course we're not responsible for knowing these shapes, but there are other molecular shapes. For example, this is sulfur tetrafluoride. And if you look at this shape, you can easily guess that this central atom has 5 pairs of electrons around the central atom, and it just happens to have 4 of those pairs occupied with atoms. And if we have all 5 electron pairs occupied with atoms, we have something like this phosphorus pentachloride shape. Or if we have 6 pairs of electrons around the central atom, we have the resulting sulfur hexafluoride. So there are other shapes that are present, and there are some very unique geometries. Thank you for watching this screencast.